All right, guys, welcome to our particle motion review notes. These are a common type of FRQ question where they talk about a particle that's moving along some kind of a horizontal or vertical axis. Typically what they'll do is they will give you a velocity function. That is not a highlighter. Let me try that again. But they could give you a position function also sometimes. They could give you the velocity function as an equation, or they could give it to you as a graph. Okay, so how do we deal with these types of questions? Well, here's the common types of questions that are given and how you would do these particular problems for each one. So what I'll do is I'm going to go through some sample problems and I'll show you how to use this little reference sheet as we go. All right, so here we go. Two particles are moving along the x-axis on the time interval from 0 to 8. The position of the particle P at any given time is this. So I want you guys to notice that this is a position function. That's important to take note of. In other words, if you were to plug in like a time value like 3, that would tell you where the particle is located on the x-axis at that time. While the velocity of particle Q at time t is given by this. So I want you guys to understand that that one, let me use a different color, this one is a velocity function. So we've got both situations here. Notice also that they are giving us an initial condition. The position of particle Q at t equals 0 is 5. And so that is an initial condition. Or you could call it a starting point, if you will. All right, so that's what we want to understand before we even begin. Let's go ahead and jump into question number 1. Question number 1 says, when is the particle P moving left, right, and changing direction? And for this, we're going to be using our calculator. So let's go back to our reference sheet here. I'm given a position function, so I know that I'm going to be in this column here. Oh, just a minute, wrong highlight. And we're being asked, when is the object moving left, right, or changing direction? So that means we're using this information here, which means that this is our how-to box right here. Now, this is a calculator-based question, so I'm going to ignore these steps for now, and I'm going to look at what it's recommending here. It says graph the derivative of P and find where it is below the x-axis. Now, if it's below the x-axis, that means it's moving left, and where it's above the x-axis, that means it's moving up or right. And now the reason for that is because P prime is the velocity of this function. Okay, so since P is a position function, when you take the derivative of that, you get the velocity. And when the velocity is below the x-axis, that means that velocity is negative. And when velocity is negative, that means you're moving left. Likewise, whenever velocity is above the x-axis, that means that you're moving in a positive direction, which means you're moving to the right. Okay, so let's go ahead and do that. Now, to find our derivative, let me bring back the question. We could do the derivative by hand, or we could just graph the derivative on our calculator. So I'm going to go with the graphing it on a calculator method here. So what you're going to do is you're going to push the y equals button, and under the y1 slot, here's what you're going to type. You're going to press math. You're going to choose 8, and at that point you'll have this little expression right here. And you have 3 blanks to fill in. Okay. In your first blank, you're just going to put an x. In your next blank, you're going to put this whole function here. and then for over here, you're just going to put an x. When you put an x here, what that's going to do is it's going to graph all the possible values of x, so you get a line. If you put a number there, you're just going to get one single point, and that will come out as a straight line. We don't want that. So this is what we're going to type into our graphing calculator. So let's go ahead and do that now. You should get a graph about like that. You'll notice that I made my y minimum -1. I made my y maximum 1. And I made my x minimum 0 and my y max 8 when I was adjusting my window. And so if you have that window, then your graph will look something like this if you've graphed it correctly. Now, where it's below the x-axis, that means my particle is moving to the left. And where it is above the x-axis, that means it is moving to the right. And so I need to find where is it touching the x-axis. Now, we might get a little jumpy here and say it's touching the x-axis at 1. It sure looks like it is, and maybe it is. But we want to be sure where it's touching the x-axis. Maybe it's touching like at 0.99 or something. So we want to be sure. So what are we going to do? We're going to press second. We're going to press Calc. We're going to choose 5 for intersect. We're going to scroll to where this point is, and then you're going to push enter 3 times. So let's do that. Second, Calc, Math, scroll to where it's crossing the x-axis. Oh, you know, I forgot. If you want to do that, then you need to actually graph the line, the x-axis. So I'm going to do that really quick. So go back to, but before we do that, let's back up a little bit. Sorry, my bad. Before we do any of that, let's go back to y equals. And under the y2 spot, let's type 0, because that's the x-axis. So I want to graph another function here. Now once that's done, now you can do the steps that I said a second ago. We can find where the graph of our derivative is crossing the x-axis. So you're going to push, once again, second, Calc. You're going to choose option 5 for where they intersect. You're going to scroll to where it's touching the x-axis, and you're going to push enter 3 times. We'll let our calculator find that point. And sure enough, it is at 1. And so now we can answer the question, when is it moving to the right and left, and when is it changing direction? And I'll also show you guys how you should write your answers here. Because on an FRQ, you need to know how to explain your answers. So you would say, since P prime, that's what we graphed, is less than 0, in other words, it's below the x-axis, on the interval 0 to 1, P is moving to the, actually we shouldn't, oh yeah, P is moving to the left, on that interval. Now I just realized I probably shouldn't be saying P. I should probably be saying X sub P, because that's the variable they gave me. So we do have to be careful that we're using the variables that the problem gives us. You could also just say particle P, but I like this notation. So you guys can imagine how I'll write the same thing for moving to the right. We'll say since x sub p prime is greater than 0, in other words, above the x-axis, on the interval 0, I'm sorry, not 0, it's 1 to 8, x sub p is moving right on that interval. Now they also want us to say when it's changing directions. Well, that's obviously where it's crossing the x-axis. That's where we're going from moving to the left to moving to the right. So we would say since x sub p prime changes signs, at x equals 1, x is changing directions at that point. Okay, so now really what I've done here is I put 3 questions into one, but I wanted you to see how you can answer it and give an explanation for your answer as well. So most of the time if they ask you a question, they'll ask only one of these things, like this one, and it would probably be worth about 2 points. You get 1 point for identifying the interval and another point for your explanation, which is the rest of the words that are up there. Okay, so let's go ahead and move on to number 2. Number 2 says, on what interval is particle Q moving to the left or right? And for that one, we're not going to use a calculator. Now, particle Q, as you guys may recall, is a velocity function. It's not a position function. And they don't want us to use a calculator. So back to our reference sheet here. We're working with a velocity function and no calculator, but I want the same question to be addressed. So no calculator means we're going to use the number line test with the v function. All right, so that's our goal, our plan of action here with question 2. So here's how you would do it without a calculator and a velocity function. You're going to take your velocity function and you're going to set it equal to 0. And you're going to factor and solve. Now, I think I'm going to make a little bit of change on this because I want this thing, oh, it's 15. That will factor nicely. Okay, I thought it was 5. All right, so we'll go ahead and factor it. I was going to change it if it wasn't factorable because I didn't want this to be worse than it needs to be. But it is factorable, so we can factor that into t minus 5 and t minus 3. You're going to set both of those equal to 0, and then you're going to solve. This one gives me t equals 5. This one gives me t equals 3. And then we do our number line test. So we're going to put a 3 here, we're going to put a 5 here, and we're only going from 0 to 8. So I have 4 intervals that I need to test. Okay, so I'm going to plug a number here into my velocity function. I'm going to plug a number here into my velocity function. And I'm going to plug a number here into my velocity function. Now, you would just plug them in here and see what you get. Now, I'm not going to show my work for that, but I will tell you at least what their signs come out to be, because that's all that really matters. If I were to plug in 1, I would end up with a positive number as an outcome. If I were to plug in 4, I would get a negative, and if I were to plug in 6, I would get a positive. And so what that means is that on the interval from 0 to 3, the particle is moving to the right, and on the interval from 3 to 5, we're moving left, and then right for the last interval there. Okay? Now, this is good work to show. You should show all that work, but that doesn't qualify as your explanation, right? We still need to be able to give them their explanation, and the explanation is going to look pretty similar to the last one. So here's how we're going to say it. We're going to say, since v sub q is less than 0, in other words, it's negative, on the interval 3 to 5, q is moving left on that interval. Likewise, we could say since v sub q is greater than 0 on the intervals 0 to 3, and also on the interval 5 to 8, q is moving right on those intervals. Okay? Finally, we can address the third question, when is it changing directions? We could say, since v sub q changes signs at t equals 3 and t equals 5, Q changes direction. At those points. And once again, you're looking at 2 points for the answer. I'm sorry, 1 point for the answer and 1 point for the explanation. All right? So that's changing direction, left and right direction, or up and down direction, what have you. Let's go ahead and move on to question 3. Question 3 says, find and interpret what x double prime of 3 is. So let's go back to our reference sheet here. So we're talking about the x sub p function, and the x sub p function was a position function, so we're in this column, and I'm looking for where the second derivative is. Well, here's the second derivative, and what does that mean? Well, that's the acceleration of the particle at that point in time. All right, so back to the question here. Let's find x double prime of 3. So basically, we already know what the interpretation is going to be. This represents acceleration, and that's going to be one of the points that we earn. But we now need to actually find x double prime of 3, and that part's going to take some work. Our calculators, as far as I know, don't have a double prime option. So what we're going to have to do is we're going to have to start by finding the first derivative by hand, and then we could use our calculator to find the second derivative. So let's find the first derivative by hand this time. And that's going to require us to use the chain rule because ln is the outside function and everything else in there is the inside function. So when you take the derivative of an ln function, you get a fraction basically, and everything inside the parentheses just goes to the bottom. So that's the derivative of the outside. The derivative of the inside we're going to put on the top. So the derivative of the top there is 2t minus 2. Okay, now we could find the second derivative by hand if you wanted to, using the quotient rule. But at this point, I'm just going to use a calculator. So from the home screen, here's what I'd like you guys to do. You're going to push math. You're going to push 8. And at that point, you'll have this little expression come up. What you're going to do is you're going to put the first derivative in here. And so when we take the derivative of that, that's going to give us the second derivative. On the last, since we want to find out what it is at x equals 3, we're going to put a 3 in here. So let's go ahead and do that and see what we get. And I get 0.059. Okay? And let's interpret that now. So t is the time. So we would say at t equals 3, the acceleration of particle p is 0.059. And I'm not going to include any units because they're not giving me any units. They're not saying whether this is measured in feet per second or what. So this is good enough for an interpretation. What really matters is you recognize that that is an acceleration. All right? So that's finding acceleration. Let's go ahead and do the next one here. This one says, find and interpret v prime of 3. All right, so back to our reference sheet. When we're talking about, this is v prime of q, right? We're using the q function, and that one is a velocity function, so we're here. And v prime is also acceleration, all right? So it's the same question, just worded a little bit differently because we're working with a different kind of function. So for this one, I think I'm gonna choose to not use a calculator. You could. So you could just, do the math 8 and find the derivative of this and plug in 3. But I think this is pretty easy to find the derivative without a calculator. So the derivative without a calculator is this. So v prime of 3 will be 2 times 3 minus 8, which is negative 2. And so what would our interpretation be for this? It would be at t equals 3, the acceleration of particle q is -2. All right? So notice that if you have a position function, the second derivative gives you acceleration. But if you have a velocity function, the first derivative gives you acceleration. All right? Let's move on to question 5. Question 5 says, determine if particle P and Q are speeding up or slowing down. So let's go back to our reference sheet here, and let's look for where we're talking about speeding up or slowing down. Well, that's right here. Now, they want us to do it for both P and Q, which means we're dealing with a velocity function and we're dealing with a position function. The position function is what we'll use for particle P. The velocity function process is what we'll use for particle Q. So let's go ahead and begin here. So for particle Q, let's start with that one. It says find where V is positive and also find where V prime is positive, and where they have the same sign, it's speeding up. Where the signs are opposite, it's slowing down. So let's go back over here. So basically you want to do a number line test for both acceleration and velocity. So let's do particle Q first. So for particle Q, we've already done a number line test for that. It looked like this. We had 0, 3, and 5, and 8. We found out that it was positive here, negative here, and positive here. Now, if you missed that, we did that back on question number 2. Right? Now, we want to do the same thing with acceleration. We want to do a number line test for acceleration. So the derivative of the velocity function was, we did that also back on the very last question. It was 2t minus 8. So v prime is the acceleration, and that was 2t minus 8. So we're going to set that equal to 0 and solve. And that's 4. Now let's pick some numbers and do the second derivative. So I need to plug a number in here. So let's go ahead and do v prime of 1, and we'll pick a number from here. We'll do v prime of 5, and we'll see what we get. If you plug 1 into your derivative of velocity, you're going to get a negative number. And if you plug in 5, you're going to get a positive number. And so what that means is that over here we've got a negative and over here we've got a positive. Okay? Now I'm going to draw some vertical lines here to break everything up. Draw a number through each number on each line. We see that on this interval here we have a negative and a negative. On the next interval over we have a negative and a positive. And on the next interval over they're both positive. So anywhere where they have opposite signs, we're slowing down, and anywhere they're the same sign, it's speeding up. So how would we write our answer for that one? Here we go. We would say we would say particle Q is speeding up when v sub q and v prime sub q, in other words, the velocity and acceleration, have the same sign. This happens on the following intervals, here and here. So that happens on the interval from 3 to 4 and the interval 5 to 8. Okay, so that's where it's speeding up. Likewise, we could talk about where it's slowing down. Particle Q is slowing down when v and v prime have opposite signs. And this happens on the following intervals, 4 to 5 and 0 to 3. Okay, there's that. Now, let's go ahead and move the discussion along to the other part, because they wanted us to not only do particle Q, but they also wanted us to do particle P for the same question. Okay, now we're going to pretty much approach it the same way. Back on question number 1, we graphed particle P's velocity function, and it looked something like this. And we found that right here is where it changed at t equals 1. And we saw that anything to the left of that, it was negative, and anything to the right of that, it was positive. And so from that, we can conclude that for particle P, the velocity given by P prime looks like this. We're going from 0 to 8, and there's a 1 here. And we know that from 0 to 1, the velocity was negative, and then from 1 to 8, it was positive. All right? Now we need to find the second derivative of P, which is its acceleration, and do a number line test for that also. All right? So how can we do that? Well, we found our first derivative a little while back. We found it was something like 2t minus 2 over t squared minus 2t. Let me look at the equation. I forgot it. Plus 10. That was the first derivative anyway. But I need the second derivative. So what I'm going to do is I'm going to graph the derivative of this function. So how do we graph the derivative of that function, and why will that help? Well, first of all, let's talk about why it helps. If I graph that derivative, I can find where that function is positive and where that's negative by looking at where it's above and below the x-axis, just the same way I did with the first derivative. All right. Now, how do I graph the derivative of that function? Well, you're going to go to y equals, and under y1, you're going to type the following. You're going to push math. You're going to choose 8. And at that point, you will see this expression again. We're going to put this function in there, and then we're going to put x equals x to graph that first derivative, or the derivative of that first derivative, which is the acceleration. So let's do that. Now, if you've graphed it correctly using the same window we had before, it would look something roughly like this. It looks like it's crossing pretty close to about 4, but we're not sure, so we're going to check to see. So once again, under y2, let's go ahead and put 0 in there. We're going to find where it intersects the x-axis. And sure enough, it's 4. And so I'll put a 4 on here. Now I see that for everything to the left of 4, it's above the x-axis, so the acceleration is positive on that interval. And anything after 4, it's below the x-axis, so that means the acceleration is negative. And so now I want to find out, when do they have the same sign, the acceleration and the velocity, because that'll tell us when it's speeding up and when it's slowing down. So I'm going to draw lines through my numbers here, and we'll see what we got. So here they're opposite, and here they're opposite. So we could see that P prime and P double prime are opposite signs on the intervals 0, 1 and 4, 8. So, and I'm using the bad notation. This is supposed to be x's over here, guys. Put those there. So, particle P is slowing down on those intervals. Whereas we could say that xp prime and x double p prime have the same sign on the interval from, oh, actually, it looks like they're never the same. So we would just add that in here. I just realized that they're opposite signs everywhere. They never seem to have the same. Oh, you know what they do? They do. Sorry, I'm being kind of goofy here. This was supposed to be a plus. This whole interval up here was a plus. So they have the same sign on the interval from 1 to 4. So P is speeding up there. Okay, that takes care of question number 5. Let's go ahead and move on to question number 6. Question number 6 is asking us to find the position of particle Q at t equals 3. It's a calculator question. Particle Q is a velocity function. So let's go to our reference sheet here. Under the velocity side, we're going to look, how do we find the position? Well, it tells us right here, you're going to use this little formula here. Okay, so that's what the initial condition was given to us for up there in the beginning. In the beginning, they told us that at time t equals 0, the position of particle Q is 5. So that's going to come in handy in just a moment. So here we go. So the position of particle Q, we'll just call it Q, at 3 seconds is equal to its initial position plus the integral from 0 to our final time of its velocity. And so I'm just going to be putting that in my calculator. Now we want to remember that Q of 0, they told us the starting position was 5, so that's what's going to go there. So I'm just going to be typing this into my calculator on the home screen and see what I get. And I'm getting out of that 23. Now it's possible that they would ask you to do this question without a calculator. The function for the velocity of particle Q is not that difficult to integrate. It does take time to do it. So it's possible they do that, but for the sake of time, I just wanted to demonstrate the process there. All right, so for question number 7, another common question that's asked is, are the particles moving toward or away from one another? I don't know if I did that on my reference sheet for these types of questions. Oh, okay, I did. It's right here. So is the particle moving toward or away from something? When you do that, you need to know the object's position and its direction. So like, for instance, let's say that I know the object is here and it's moving in that direction. Well, then I'll know if it's moving towards something. So if I have an object over here, then it's moving towards it. But if I have my object over here, it's moving away from it. And so you need to know both the position and the direction of the particle if you want to know if it's moving towards something or not. So for question 7, I want to know what's up with particles P and Q. Are they moving toward or away from each other? Well, I need to find the position of particle Q. I need to find the direction of particle Q. I also need to find the position of particle P, and I need to find the direction of particle P at t equals 3. So I've already found the position of particle Q at 3. That was question number 6. We found out that that was 23. Now what is the direction of particle Q? Well, that would be found by plugging 3 into the velocity function that they've given us. So go ahead and plug 3 into the given velocity function for particle Q and see what you get. Now I get 0. That's interesting. So what this means is that if I were to put this on a number line, like let's say here's 0, well, particle Q is way over here at 23, and at that instant in time, it's not moving, because if I had a positive number there, it'd be moving to the right, and if I had a negative number, then it'd be moving to the left. but since it's 0, it's not moving at that point. And that's actually because of what we saw in one of our questions earlier where we found where particle Q is changing directions. It changes directions at t equals 3. So at that point, it's neither moving left nor right. Now let's go ahead and find the position of particle P. To do that, I'm going to take the position function for particle P, which was given, and plug in 3. So if I do that on my calculator, I will get the following. And I get 2.773. Okay, so that's about right here. So we'll call that P, and we'll call that 2.773. That's about where particle P is located. Now I need to find out which direction particle P is moving. So I need to find out what the velocity of particle P is at 3, because that will tell me the direction. So now I'm going to plug 3 into the velocity function for P. Now, you could either use the one that we've already found earlier. Actually, it was a 2. You could use that, or you can just do the derivative formula using math 8, plugging the original position function in. It doesn't really matter which one you plug 3 into, but go ahead and plug 3 into that and we'll see what we get. And I'm getting 0.308. Now that's a positive number, so that means it's moving to the right. So are the particles moving toward each other or away? Well, Q is not moving at all, but P is moving towards Q. And so we would say, since Q is at x equals 23 and not moving, while P is at 2.773 and moving right at t equals 3, they're moving towards each other. You still need to show all your work, but here's your official explanation for that. Okay? And there you guys have it. So, all right, let's go ahead and move on to question number 8. The question is, how far is particle Q from its starting position at t equals 8? So, to find how far away it is from its starting position, I wonder if we have something like that on our reference sheet. Let me see. Well, there it is. It's the displacement formula here. So basically, we're just going to do the integral of the velocity from 0 to 8 on our calculators. So that's pretty simple. We're going from 0 to 8. Now, another way that we could have done this question would be to have found the position of the particle at 8 and then subtracted that from the starting position, which was 5. But this will work too. So let's go ahead and punch that into our calculator to find how far it is from its starting point. Another way that might be asked is they might say displacement, because that's what displacement is. But if we were to type that into our calculator, we would get, and there you guys got it. All right, next question. What is the displacement of particle P? All right, well now particle P is a position function. All right, particle P is a position function. So if you want to find the displacement of a position function, then you're going to have to integrate its velocity, or its first derivative, from your starting position to the ending time. So let's go ahead and do that. Now another way you could do this problem is you could find the starting position and the ending position simply by plugging in the numbers here. You could plug 8 into your position function and 0 into your position function, and that will give you the answer, because this is your starting position and ending position. Subtract them, that'll tell you the displacement. Or you could just do the integral of the derivative of the position function there, and you'll get it. I think I'm going to go with this approach. It's a little bit easier, but the other way would be to do the integral from 0 to 8 of 2t minus 2 over t squared minus 2t plus 10. They would both give you identical answers. So for me, I'm just going to do the one on the bottom there because it's a little bit easier. So to do that, I'm going to enter my x sub p function into the y1 slot. And then I'm going to go back to my home screen and I'm going to push vars. I'm going to bring up y1 and I'm going to plug in 8. And then I'm going to do vars. I'm going to bring up y1 again and I'm going to do 0. And whatever I get for those two things, I'm going to subtract them. So let's do that. So for x sub p of 8, which would be like on your calculator y1 of 8, I get approximately 4.06. 4.060, and for x sub p of 0, I get approximately 2.303. So if I took those two values and subtracted them, I would end up with roughly 1.758 as the displacement. Okay, and all that basically tells you how far the ending position is from the starting position. And since it's positive, that means the ending position is to the right of the starting position that much. All right. Moving along to our next question, we have, what is the distance that particle Q traveled? All right. Whenever you want to find the distance and you're given a velocity function, all you have to do is the integral of the absolute value of your velocity function from 0 to 8. So let's go ahead and punch that into our calculator and see what we get. And I get about 37.3. So that's the distance traveled by particle Q. Now, for particle P, it's the same thing. You're going to integrate the absolute value of something from 0 to 8. But since we have the position function for P, we need to put its derivative in here. So I'm going to put 2t minus 2 over t squared minus 2t plus 10 there. And we'll see what we get for that one. And for that one, I get 1.758. Okay? And so those are the, pretty common types of questions that you could be asked for these types of FRQs. So hopefully that's helpful, and we'll put the stuff into practice tomorrow. See you then.